Hello, my name is Adam Lerer, and I'm going to be talking about Pytorch-BigGraph, which is a system for training embeddings of very large graphs. And this is joint work with Lidell Wu, Jiajun Shen, and Abhijit Bose, who are here, as well as some other colleagues at Facebook AI Research. So first, I'm going to talk to you a bit about what graph embeddings are and why you should be interested in training embeddings of very large graphs. And then I'm going to talk about some of the modifications that we make to traditional graph embedding systems in order to scale to very large graphs. And then finally, we'll look at some experimental results about the scaling of this system. So first of all, an embedding is a learned map that maps from some kind of entity to a vector of numbers that encodes some notion of semantic similarity between these entities. So most people who have heard of embeddings would probably have heard of word embeddings like word2vec. And in word2vec, that type of embedding, you learn a vector of numbers for each word such that you can predict a word in a corpus of text from its context. And what happens there is it's this unsupervised method where you just train it on a corpus of text and you learn features for each word that encode the semantics of those words. And you have a similar notion for graph embeddings. And in graph embeddings, what you're trying to learn are vector representations of each node in a graph. And you train them again with stochastic gradient descent on these vectors with the objective that nodes in the graph that are connected have more similar embeddings than nodes that are not connected in the graph. Since actually in this paper we're going to be looking at multi-relation graphs, it's a little bit more complex than that, but essentially you're computing a similarity metric or some score for edges in the graph that should be higher for edges in the graph that exist than potential edges that do not exist. I also want to mention, because I got some questions about this, that graph embeddings are not the same as graph neural networks. Graph neural networks are a parametric supervised learning method on graphs where you have labels for nodes and you're trying to predict them based on features of the nodes. Whereas graph embeddings are actually trying to just take in a graph and learn features for each node that encode this similarity based on the context that these nodes occur in. So the reason that you might be interested in learning graph embeddings is that they're a form of unsupervised learning on graphs, and what you end up with is a set of task-agnostic node representations or features that you can use for a number of downstream tasks. Because like most ML tasks like classification and clustering, you can't operate directly on graphs, but they can operate on features that you can learn from these graphs. And things like nearest neighbors are semantically meaningful, so you can take these features from this graph and say, I know about this node I'm interested in, tell me other nodes that are like this. So this is the only slide that's going to include math, so I just want to give a little bit more of the formalism of these models. I've included references to some of the models that are going to be encompassed by this kind of general class. But what you're basically doing is you're computing some loss between the score for an edge that exists in the graph and a negative sampled edge, some edge that doesn't exist in the graph. So here I'm showing a margin loss, where f of e is the score for an actual edge in the graph, and f of e prime is an edge that doesn't exist in the graph. And here you're just trying to optimize a margin loss that tries to make the score for a real edge higher than the score for a non-existent edge. And the way you compute this score is some similarity metric that combines the source embedding, the embedding of the source node, the embedding of the destination node, and some embedding of the type of relation that you're encoding. So in this example, you look at the cosine similarity between the embedding of the source node and the sum of the relation and the destination embeddings. And the way you construct these negative samples is by taking a real node in the graph and replacing either the source or the destination entity with some other node. So for this node BC, which is in your data set, you're going to construct negative samples like BE and BA, as well as negative samples such as AC and DC. So these multi-relation graph embeddings are studied across a number of different types of data sets. The way it's most commonly studied is in terms of knowledge graphs. So for example, if you considered Freebase as the structured information, or Wikidata is like the structured version of Wikipedia that shows all the connections between the entities of Wikipedia, like Hawaii is a state in the United States, Barack Obama is the president of the United States, and so on. But people are also interested in a similar problem for recommender systems, which is a more supervised task where you have connections between like, ratings of movies, and also for social graphs where you're interested in propagating kind of the attributes of people in some social graph based on homophily, based on the fact that people who are connected in a social graph have similar attributes. But the graphs that we're interested in are slightly different. They're somewhat related to this class, but the type of graph that we're more interested in is like, imagine you have a music streaming service. You really have this very large graph where you can think of all the users and all the songs and genres and albums and artists as nodes in this graph, and then you have a number of different types of relations where you can look at an edge in this graph for like every song that a user has listened to or bookmarked or bought, and you also have parts of the graph that for different types of entities that correspond to like an artist that produced a song or how artists collaborated. And if you train a single embedding of all of these different entities in a single space, you can ask really interesting questions like, tell me which genres are similar, even though you don't have any explicit information about the genres. Or, I have these 5 songs in French, tell me about some more songs that are in French. I want it to predict other songs that fit into the same class, just by using like nearest neighbors, for example, on these embeddings. But the thing about these types of online interaction data sets is that they're really big data. So web companies have data sets like this that could have billions of nodes and trillions of edges. And if you think of a graph that has 2 billion nodes and you just pick an embedding size of 100 dimensions, you now have an 800 gigabyte model, which doesn't fit in even CPU memory, let alone on the GPU. And then when you look at graphs of this size, training speed is also an issue. When I'm trying to train on a data set of size 1 trillion, training speed is also obviously an issue. So we want to ameliorate both these problems. So the main approach we take with Pytorch-BigGraph is a similar approach to many ways of speeding up graph algorithms, which is you do a matrix blocking to subdivide the graph. So what you do is you take every node and you pick some way of sharding them into n groups. So you could just say you uniformly assign an index 1 through n for each node. And what this means is that every edge is now divided into one of n squared buckets based on the source and destination node shard. So, if you think of bucket 3.1 here in red, that is the edges that belong in there have their source node in shard 3 and their destination node in shard 1. And what this buys you is that if you, for example, if you want to train on a single machine, you get this temporal locality property where you can train on this whole bucket of edges in 3,1, and you only need to store part of your model in memory, like the embeddings for shard 3 and shard 1, and everything else can be swapped out to disk. And then it also means that you can do distributed training because different buckets that use different parts of the model can be trained in parallel without having to do any synchronization after every SGD step with a parameter server. You just do them completely, you can do them almost completely in parallel, and you only have to do communication between the machines when a machine starts working on a different bucket, because then it has to transfer that part of the model from one machine to another. So I would point out that this is not a lossless modification to the training objective. There are 2 ways in which this modifies your training. One is that you're no longer sampling edges independently because you're working on one bucket of edges at a time. And there are theoretical results that say that this kind of non-IID sampling of your data still converges to the same result, but it may converge slower. And second of all, the distribution of negative samples change, because if I'm looking at an edge in one bucket, I can only construct negative edges out of that same bucket. So we do have to validate empirically that these modifications still produce similar quality models. So I'm going to talk a bit about how we do the distributed training in Pytorch-BigGraph. Basically, we need to do 3 different types of communication between the machines. And this is all coordinated. When you launch the trainers on the different machines, they all launch sub-process servers that are able to do all these different types of communication. So the first thing is that you have to synchronize which machine is working on which bucket of edges. And this is done with a lock server that assigns buckets to machines. And the way it does it is basically just trying to greedily maximize machine partition affinity. So if a machine has worked on bucket 3, 1, maybe it will next work on bucket 3, 5, so that it only has to exchange one partition of the data instead of 2. The second thing is you actually have to exchange the model partitions. And the way this is done is that when partitions of the model are not in use, they're stored in a sharded partition server that's sharded across the training machines. And finally, there's a very small number of model parameters that can't actually be sharded in this way, specifically the embeddings of the relations. And this is, you don't have very many different relation types, so this is just kilobytes or a couple megabytes of model parameters. And these are handled with your traditional parameter server, and they're just updated asynchronously with a standard parameter server model. But that's just a few, like a megabyte of parameters as opposed to the gigabytes of node embeddings. And this is all implemented with the MPI-like Pytorch distributed primitives that are used that you can construct sort of model parallel training or model parallel structures in Pytorch. And this runs on top of MPI or TCP, whatever you're running on for your distributed architecture. So there's one other thing that we do in Pytorch-BigGraph in order to improve training speed, and that is, it's based on the fact that training time is generally dominated by the negative sampling edges, because for every edge in the real graph, you typically don't just compute one negative sample, you compute 10 or 100 negative samples. And so you're kind of dominated by the time in the random access lookup of those embeddings and the computation of the scores for those embeddings. So what we do is we say, what if we take a sub-batch of 100 real edges and use the same set of random nodes to construct 10,000 negative samples instead of using different random nodes to corrupt each of those 100 edges in the batch. What this does is, first of all, it reduces the random access memory bandwidth by a factor of 100 for negative sampling. And also, you can notice that if the similarity metric is based on a dot product or a cosine similarity, then the batch of negative scores can just be computed as a matrix multiply between the node embeddings of the positive source node embeddings and the negative destination embeddings, which ends up being a lot more efficient. And what you find as a result of this is that if you do traditional negative sampling, that your training speed is, and previous work has reported this, your training speed is basically inversely proportional to the number of negative samples you use, whereas with this optimized negative sampling, you get pretty much constant training speed up to about 100 negatives. So the first thing we did, now I'm moving on to the experimental section, the first thing experimentally we looked at is just like this knowledge graph of Freebase, which is basically the standard for looking at these multi-relation graphs. And they typically work on this very small subset of Freebase that has 15,000 entities. And what we find is when we implement different models, including the state-of-the-art complex model, that in PBG we replicate or get higher accuracy on a basically link prediction or knowledge-based completion task as the original papers. The only thing that we're not replicating here is this one paper, which was from a co-author that's just like uses huge embeddings and is really fancy. And so even the co-author said that it's not worth reproducing this because the fact that you can get very high knowledge-based completion doesn't necessarily mean that these embeddings are necessarily useful on a downstream task. We actually can reproduce these, but we don't report them here. But then what we do is we train these embeddings on the full Freebase graph, and I think this is the first, at least reported result of embeddings on the full Freebase graph, which has 51 million nodes and 1 billion edges. So on the right, you see a t-SNE plot of some of the nodes based on the full Freebase embedding, and what you see is you have a clustering at the top of different professions, a clustering of numbers, a clustering of countries. And this is just a very small subset, but you have like basically every entity in Wikipedia embedded in this same space. And what we show is that as you partition the graph more finely, you use less memory down to, with 16 partitions, you use, 8x less memory while achieving the same performance and mean reciprocal rank, which is the metric you use for these tasks. Next, we look at parallel training, and the results here are more mixed on knowledge graphs, because what we find is we get, reasonable parallelization up to 4 machines, but then we start to observe model degradation above that. And in general, we found that for knowledge graphs, parallel training is quite finicky for a couple reasons. One of them is that you have a very large number of relations compared to most of the graphs we look at, and so the parameter server has to synchronize all of those. And just the structure of these graphs is quite complex. And so when you actually look in terms of time, the improvements are kind of modest, and I wouldn't necessarily use this on a knowledge graph I wouldn't necessarily use parallel training for knowledge graphs. However, across a number of different data sets that we tried that were more like social graph data sets, for example, Twitter, we find that they're not finicky in the same way, and pretty much like no matter how we train them, we get close to linear speedups with no degradation in model quality with partition and parallel training. We speculate there are several reasons why these graphs are different, but I'm not going to speculate too much on that here, but say that we kind of leave that to future work of untangling the different causes of model degradation in knowledge graphs and maybe ameliorating them. But to be honest, knowledge graphs are not really the purpose of Pytorch-BigGraph, and we found in most of the data sets that we're actually interested in that this hasn't been a problem. Some other things that I think are interesting future work. One is looking at how to do parallel training for graphs that have featureized nodes. So like either bag of words, if you have a node that's a description of a song, right, then you would want to do bag of words embedding of that text as part of the graph. And we do actually support this for single node, but thinking about how to parallelize that is an interesting direction for future work, as well as like dense node attributes. And finally, I think that there's a really interesting direction of future work where you can apply the same techniques to also do GPU training, because currently this only runs on the CPU, because GPUs have like another 10x lower memory capacity, but you could do the same kind of matrix blocking hierarchically. And so on each machine, you're then going to subdivide the nodes even further and do parallel training on multiple GPUs where you swap the different shards across the GPUs to do multi-GPU, multi-machine training. So that's basically the end of my talk. The code and embeddings just got released. The code and embeddings for Wikidata, which is this knowledge graph, were released today, so please check it out. I just want to mention that I think the world is full of big graphs. Things like online interactions, Bitcoin transactions, medical records, purchases, biological networks, and so on. And we've really only looked at a couple things here. And so I hope people try this out for other kinds of large graphs. Pytorch-BigGraph is really designed for graphs that are quite a bit bigger than even the largest currently available public data sets. So we kind of hope that this spurs people to work on even larger data sets and look at graph embeddings for bigger data. Thank you.
Thank you. Questions?
My name is Sefaridi from Sweden. Just a general question. This graph embedding, I mean, normally people use distributed graph frameworks or graph databases to solve problems on graphs. What these kind of techniques will give more than what's existing today?
Yes, so there are a lot
I mean, you can do a lot of things by these distributed general frameworks with graphs or graph databases and so on.
Yeah, that's true. So for a lot of like traditional graph metrics, if I want to find like the min cut of a graph or even an SVD of the graph, which is somewhat similar to what we're doing here, there are existing kind of distributed graph frameworks that do this. But what this is basically providing is, first of all, these kind of multi-relation graphs aren't really handled by any existing system. And it's not clear that they could be. And in general, what we kind of want here is that you can put in any kind of loss function you want for SGD, and you can train kind of generic multi-entity, multi-relation graphs, for where in PyTorch, like you have automatic differentiation. So I pick any model I want, right? Just write down your model, and then what you get here is that you can train kind of generic models via SGD with automatic differentiation and negative sampling. These aren't really capabilities that are built into these other frameworks, even though they might use some of the same kind of distribution methodology.
Hi, I'm Min Jie from NYU. Really nice work. So my question is, what's your opinion about those graph embedding algorithms based on random walk and graph sampling, such as deep walk and Node2Vec? And can Pytorch-BigGraph actually support that very easily, or you think it requires a significantly different system design?
Yeah, that's a good question, and we do talk a bit about this in the paper. So deep walk, there are kind of two different classes of algorithms for graph embeddings. One of them kind of looks more like Word2Vec, where you do random walks in the graph and try to construct embeddings based on that, or this one which is more for knowledge graph embeddings. The deep walk stuff has been more used for social graph embeddings, and it's kind of earlier work. And we actually compared on some of the data sets right out of the deep walk paper, and we found that both on the original task they proposed and for downstream unsupervised tasks that these knowledge graph embedding methods performed as well or better than the deep walk type embeddings. They performed a lot better actually on downstream unsupervised tasks, and we found that they were orders of magnitude faster. So I actually have some plots here about this. So here we compare to deep walk actually, and we find that the red line is our graph embeddings, and this is looking at link prediction, which you may not say is necessarily fair because that's what deep walk, not necessarily what deep walk is made for, but if you look at the YouTube data set, which is what they actually test on, we also do better than that at downstream tasks. So I think there are classes where the deep walk type embeddings might be better, but for the things we've looked at, they haven't been.
I see. So another small technical question is when you do negative sampling and when you process one edge block, how can you avoid get these negative samples that appears in other edge blocks?
Right, so we don't actually, the negative sampling doesn't explicitly exclude edges that are in the training set. So what you find is that these graphs are very sparse, so it's not usually an issue of just picking random negatives. It is the case that how you choose your negatives is one of the most important things, and there's stuff we talk about exactly what distribution, just like in Word2Vec, the distribution of negative examples that you choose ends up being very important for how generalizable these are in downstream tasks. So we talk about that a bit in the paper.
Okay, thank you.
June from UC Berkeley. So the interesting thing about graphs is that I'm particularly interested in how you sharded them. So graphs have a huge number of nodes that have very little information, very little edges, and few nodes that have lots of edges, etc. Did you take that into account when determining the sharding? I would love to hear more about what things you tried with the sharding, what worked, what didn't.
Yeah, it's a good question, and it's something that we thought quite a bit about. But actually, there's a bunch of trade-offs in how you do that. What we end up doing is just uniformly sharding nodes. But another thing you could do is shard by degree, and there's kind of trade-offs there. But for example, you'd think that sharding, one thing you end up with if you shard not uniformly is that you get load imbalance across your across the different buckets, which is something you don't want. But one thing that we've thought about might be better about sharding, let's say by degree, is if you first do the high degree edges first, then you might get a better layout of the embedding space. And then you can add in the lower degree edges, which don't affect the final layout as much, and that's something that we're experimenting with.
And that begs a follow-up question. Did you do any pruning on the data set to determine what was eligible for going into the embedding?
That's a good question. It's not something that we explore in the paper, but it's definitely something that we've looked at, internally. And there's a interesting trade-off that I think is an important direction for future work about where do you cut off? First of all, where do you cut off how do you prune what you use for the embedding? And then how do you propagate the embeddings from the part of the graph you do train? It's a little bit more obvious in a single relation graph that you can just sort of average the embeddings of your neighbors to get the embeddings of the things that have low degree. It's less clear for a multi-relation graph how to do that or what's the optimal strategy for doing that.
Thanks.
But that's a great question. And it's something.
Cool. So let's thank the speaker again.